Hello there guys, today we're going to be solving IB Math AAHL paper 1, no calculator. Not too bad of a paper, but it does need some critical thinking on some questions, so let's jump right in. Starting with question 1, we are given a function g of x, and we are asked to find g dash of x. So basically, the first derivative of the function. So let's go right ahead by writing out g of x is equal to e power x squared plus 1, and g dash of x, we're going to have to use the chain rule. So d by dx of x squared plus 1 times e power x squared plus 1. This is going to be 2x e power x squared plus 1. And we'll write out here by chain rule to make sure the examiners know exactly what we're doing. So since that is g dash of x, now we can solve for g dash of minus 1, which is 2 times minus 1 e power 1 squared minus 1 whole squared plus 1, which is equal to minus 2 e power 2. So g dash of minus 1 is equal to minus 2 e squared. Perfect. Moving on to question number 2, we are given a circle with diameter AB, where A has the coordinates 1, 4, 0, and B has the coordinates minus 3, 2, and minus 4. So let's go ahead and draw this out. So if this is our circle, let's call this point A and this point B, and this is minus 3 to minus 4, and this is 1, 4, 0. Now, first we are asked to find the center of the circle, and the center of the circle, let's write out here, center of circle is midpoint of diameter. And since we are given the diameter points A and B, we can solve for the center, O. So center O is equal to 1 plus minus 3 by 2, comma, 4 plus 2 by 2, comma, 0 plus minus 4 by 2. And this gives us a total of minus 1, comma, 3, comma, minus 2. And this is just by midpoint formula. So we have our center O is equal to minus 1, 3, minus 2. Let's put a box on that. Next, moving on to part 2, we are asked to find the radius of the circle right here. And the radius of the circle can simply be found by the three-dimensional distance formula, which is root over x1 minus x2 whole squared plus y1 minus y2 whole squared plus z1 minus z2 whole squared. And this is essentially like the three-dimensional Pythagoras theorem, and you might hear me calling that other times because that's how I like to remember it. It's okay if you have a different way. So let's call this r is equal to root over, yes, so we'll start with minus 1 minus 3 whole squared plus 3 minus 2 whole squared plus minus 2 plus 4 whole squared. So overall, this gives us r is equal to root over 2 squared. Oops, this is minus 1 plus 3, guys. So 2 squared plus 1 squared plus 2 squared. Therefore, r is equal to root over 9. R is equal to 3. Now let's move on to part D. We are asked to find the exact volume of the cone. So for this, I'm going to write out the points on this diagram. 1, 4, 0, minus 3, 2, minus 4, and we're given our vertex coordinates as well. Minus 1, minus 1, 0, And let's go ahead and write out our center points as well, which is -1, 3, -2. Now, the volume of a cone is equal to 1 by 3 I r squared h. Now, we don't have h, we have r. So to find h, let's take this distance. H is equal to square root of basically the distance between this vertex and the center O, which is 0 squared plus 4 squared plus 2 squared, which is root 20. So let's write that out down here. So first things first, h, oops, color, h is equal to root over -1 minus -1 whole squared plus 3 minus -1 whole squared plus -2 minus 0 whole squared, which is equal to root over 4 squared plus 2 squared equal to root 20. So V volume is equal to 1 by 3 I 3 squared root 20, which is 3I root 20. And now we simplify. We can take root 20 is equal to 2 root 5. So therefore V is equal to 6 pi root 5. And that's your final answer. Moving on to question number 3. We are given 3 values and an equation, and we're asked to prove that the equation is true. So for this, anytime you have this kind of an equation, you can simply use RHS is equal to LHS. So let's take the right hand side first, is equal to a squared plus a squared minus 1 whole squared by 4, which is a squared or 4a squared plus a power 4 minus 2a squared plus 1 by 4. I just got this 4a squared by moving the a squared to the numerator. And this means that the right hand side is equal to a power 4 plus 2a squared plus 1 by 4. Now let's look at the left hand side. Is equal to a squared plus 1 whole squared by 4, which is a power 4 plus 2a squared plus 1 by 4. And since the right hand side is equal to the left hand side, equation is true. So it's a very simple question, guys. Just make sure to show your steps and try not to skimp here because it's a whole 3 marks and you don't want to lose anything for not showing your working. So next we're asked to find an expression for the area of the triangle when these are the lengths of the sides. So if we were to draw out our triangle right here, let's draw it out here in our blank space. We see that we have a 90-degree here and we have the longest side here, the hypotenuse. And you have to remember that the hypotenuse is the longest side, which means that this value is going to be your hypotenuse, a squared plus 1 by 2. The other two sides are going to be a and a squared minus 1 by 2 respectively. Now the area is equal to half base height. And from the diagram, we can take the base as a and the height as a squared minus 1 by 2. So this means that the total area is a power 3 minus a by 4. Therefore, the area of our triangle is equal to a cubed minus a by 4. Put this in a box to make sure the examiner knows, and make sure to write out from diagram below to make sure all your reasoning is shown and you don't lose marks for that. Moving on to question number 4, we are given a derivative of the function and we are asked to find the value of the function. So first, let's go ahead and take f of x is equal to integral of f dash of x. That's a very common known expression, which is equal to integral of 6x by x squared plus 1. Now, we can integrate this directly because you have an x in the numerator and in the denominator. So let's do integration by substitution. Take x squared plus 1 is equal to u, du is equal to 2x dx. And now you see that you can actually reduce the equation. So the function becomes 3 du by u, since 6x dx is equal to 3 times 2x dx, which is 3u. So let's write that in a bracket, make sure the examiner knows what you're doing, which is equal to 3 ln u, which is 3 ln of 1 plus x squared. But don't forget there's a plus c involved. So we have f of x, but we still have a constant. So to get rid of that constant, let's plug in our point, 1 comma 5. So f of 1 is equal to 3 ln 1 plus 1 plus c, which is equal to 5. This means that c is equal to 5 minus 3 ln 2. Finally, our answer for f of x is going to be 3 ln 1 plus x squared minus or plus 5 minus 3 ln 2. Now, of course, you can simplify this expression in many ways, such as combining the logarithms by saying f of x is equal to 5 plus ln of 1 plus x squared whole cubed by 8, or any other variation, but for us, we will just leave it right here. Moving on to question number 5, we are given a complex polynomial, and we are asked to find various parts. We're starting off by finding the value of alpha, considering the product of roots. So for this, you need to know Vieta's equations, which are given in the data booklet. Vieta's equations. And for that, it states that the product here, product of roots is equal to e by a, which is the constant by the coefficient of the highest power of x. So this is 80 by 1, which is equal to 80. This means that the roots of the equation, the product of the roots of the equation, is going to be 80. But you see that this is a biquadratic polynomial, which means it has 4 roots. So the 4 roots, we're only given 3. This means that we need to find that 4th root. And a property of the roots of a polynomial is that if there's a complex root, there's also the conjugate of its complex. So 3 plus I and 3 minus I, alpha and alpha squared are roots. And we'll write since conjugates of roots. Now let's take the product of the roots. 3 plus I times 3 minus I times alpha squared is equal to 8. So this means that we have 9 minus I squared times alpha cubed is equal to 80. And you guys know alpha squared is minus 1. So this is 10. Alpha cubed is equal to 80. Alpha cubed is equal to 8. And alpha is equal to 2. That's it. Then we are asked to find the value of p. Now we've already taken the product of roots. And here you can see that p is the coefficient of the second highest power of x. And you might notice that the sum of roots is equal to minus b by a. In this case, b is equal to p, so minus p, and a is equal to 1. So sum of roots is minus p. Let's go ahead and add all the roots together. p plus I plus 3 minus I plus alpha squared is equal to minus p. So let's substitute our value of alpha from here. That gives us 6 plus 2 plus 4, since the plus I and the minus I get cancelled out, which is equal to minus p. Moving ahead, this means that minus p is equal to 12. Therefore, p is equal to minus 12. That's it. Moving on to question number 6. A very interesting probability question. It's pretty basic, but you guys need to be able to use your data booklet well. we are given two cases, two events, A and B, and we're asked to find P of A intersection B with different cases. So here, when A and B are independent, we're asked to find the value of P of A intersection B. In your data booklet, you'll see a line that says for independent events, P of A intersection B is equal to P of A times P of B for independent events. So this means that P of A intersection B is equal to 0.3 times 0.8. Therefore, P of A intersection B for independent is equal to 0.24. That's it. Next, we are asked to find the minimum possible value of P of A intersection B. And for this, you need to remember that the sum of all probabilities, the probability of universal set, is always equal to 1. And you'll see that P of A plus P of B by themselves give you 1.1. This means that there must be a P A intersection B, because if not, this equation, P of A plus P of B minus P of A intersection B is equal to 1 does not hold true. So we can take 0.3 plus 0.8 minus P of A intersection B is equal to 1, and P of A intersection B is equal to 1.1 minus 1. So P of A intersection B minimum P of A intersection B is equal to 0.1. Now, let's just quickly go over why this is equal to 1. Because in your data booklet, P of A union B is used instead. But for the value to be minimum, you need to make sure that P of A and P of B take up the entirety of the universal set for minimum intersection. So we can just write that out and make sure the examiner knows we're actually thinking about it. And finally, part C, we are asked to find the maximum value. So for this, I'm going to draw out a small Venn diagram over here. So if this is our universal set, this is B, and this is A, this will be the maximum value, because then the intersection is maximum, because anymore you literally cannot have more than A being entirely encompassed by B. So max of P of A intersection B is equal to P of A, which is equal to 0.3. And so let's just say that maximum occurs when A is a subset of B, so that more values lie outside of P of A union B, or not P, but rather they lie outside of A union B. That's it. So let's put boxes around our answers, make sure that what we're doing is clear, and move on to the next question. Question number 7, we are given a curve, and we have to show that the curve has no local maxima or minima for x is greater than 0. For this, we can simply differentiate and show that dy by dx is not equal to 0 for this condition. So to differentiate, let's start off by expanding the equation. X squared y squared plus y power 4 is equal to 4x squared. Now, when you have to differentiate, you realize you might need to use the product rule here. So we take u is equal to x squared, u dash is equal to 2x, v is equal to y power 4, v dash is equal to, oops, not y power 4 guys, it's y squared. And v dash is 2y dy by dx. So when we plug this into our equation, we get, when we differentiate both sides of the equation, we get vu dash plus uv dash, which is y squared times 2x plus uv dash, so x squared times 2y dy by dx plus 4y cubed dy by dx is equal to 8x. Now this is a simple case of implicit differentiation, guys. So don't worry about it. Just keep your head cool and keep moving. So this means that dy by dx is equal to another function. But first of all, to isolate the dy by dx, we have to take it as common from this 4y cubed plus 2x squared y is equal to 8x minus 2xy squared. So dy by dx is equal to 8x minus 2xy squared by 4y cubed plus 2x squared y. Now, of course, we can simplify this by taking 2 as common. So this means that dy by dx, let's write this a little bit bigger, is equal to 4x minus xy squared whole divided by 2y cubed plus x squared y. Now, to show that there is no local maxima or minima, we can set dy by dx is equal to 0. And this means that 4x minus xy squared is equal to 0 by setting dy by dx equal to 0. Now for this, the reason that it's this simple of an equation is because the denominator entirely gets cancelled out when we do cross multiplication. So this is our equation. So let's take x out as common. 4 minus y squared is equal to 0. This means that x is equal to 0 or y is equal to 2. Plus or minus 2 or also known as y squared is equal to 4. Now, with these conditions, this actually seems plausible, but this is already wrong. Not possible, since x must be greater than 0. It's not greater than or equal to, it's just greater than. So now let's look at this case. If y squared is equal to 4, what happens to the actual equation? So x squared plus 4 times 4 is equal to 4x squared. 4x squared plus 16 is equal to 4x squared. And this means that 16 is equal to 0, which is clearly incorrect. So this means that x equal to 0 is not possible, and y squared is equal to 4 is not possible. Therefore, for x greater than 0, dy by dx cannot be equal to 0, and no local maximas or minimas exist. Hence, proven. Now let's move on to the next question. Question number 8. This is a very interesting cosine question. It takes a little bit of thinking, especially in the last part, but let's go through it real quick. So we're given this function and we are given a value of k. Find the largest value of a, which is the restriction of the domain, for which the inverse function exists. So let's go ahead and write this out. So when k is equal to pi by 2, f of x is equal to cos of x minus pi by 2. This is equal to sine of x. Now let's draw out the sine of x curve right here. Simple sinusoidal curve, 2 pi, pi, and now see that this domain is constrained from 0 to a, right? So that means that as we move along, the horizontal line test must be fulfilled. And you see the points of failure are along this side, and they stop right here. Any more than pi by 2, and the horizontal line test is failed. This means that the max value of a for the function to have inverse, for inverse to exist, is pi by 2. A equal to pi by 2 here. Part B, instead of pi by 2, we are given pi. So when k equal to pi, then f of x is equal to cos of x minus pi. Now you guys might know this as minus cos pi. So f of x is equal to minus cos x. Now, if we draw out this graph here, so yes, right here, if we draw out the graph, we see that, well, it's a terrible graph, but you guys get the point. From 0, as we draw the horizontal line, it intersects here, and so on, keeps intersecting until right here. This is where it stops. This is where the intersection points converge as we move up right here. So up till there, the horizontal line test is passed. And what is that value? Pi. So for k equal to pi, a is also equal to pi. So I'll just erase a little bit of that line, make it a little bit neater. Yeah. And now, moving on to part C, which I'm going to write over here. In your actual exam, I'd suggest taking an extra sheet or something of the sort in order to make sure that you're really clearly showing what's happening. Now for this, you're not given a calculator, but to show you how this works, I'll be using a example from Geogebra. So for this Geogebra explanation, I have plotted out a few functions, one being our main function, f of x, which is green over here, and that is going to be cos of x minus k. And I've set the variable k over here to be anywhere from pi to 2 pi over here. Now, I also put up a few intersection points over here, a, b, which are the intersections between our maxima line, which is g of y, and h, g of x and h. So both of those land up over here and are the maxima and the minima lines respectively. Now, when we look at this, for an inverse to exist between pi and 2 pi, the horizontal line function must be passed, similar to how we've done before. Now let's look at what happens as the function plays out from pi to 2 pi. We see that the inverse exists only from f to b. At whatever value of f, whatever value of k rather, the inverse exists only from f to b. So to find this, we see that it seems to increase almost linearly. And it has a minima at pi where it's equal to 0, and a maxima at 2 pi when the distance between them is exactly pi. Keeping that in mind, we can write out a function on our paper. The inverse function exists as long as a is equal to k minus pi. That is the maximum value for the inverse function to exist. Any other value will result in a smaller domain and thus a smaller constrained region. So from k is equal to pi to 2 pi, this is your pi. And as we keep going, so let's say that this is our next line. Yeah, it's like this. So let's say this is k is equal to pi by 4. Right here, or k is not pi by 4, but 5 pi by 4. Right? Yeah, 5 pi by 4. We see that a is equal to pi by 4 because once you pass right here, you'll end up with intersections up till here. So as such, a is equal to k minus pi. Moving on to question number 9. Consider the homogeneous differential equation that's given here. And it's given that y is equal to 2 and x is equal to 1. Using this substitution, solve the differential equation in terms of y squared of x. Or y squared. So for this, it's a very standard substitution. And it's not going to be too hard, guys. Just take your time with it. Don't stress out. And so let's start off by substituting y is equal to vx. This means that dy by dx is equal to v plus x dv by dx. And this can be memorized, or you can derive it on the spot using the product rule, similar to how we did it for y squared x squared. So that's how you get this. Now let's substitute in y is equal to vx into this equation. So dy by dx, which is v plus x dv by dx, is equal to y squared, which is v squared x squared minus 2x squared whole divided by x squared v. Now you can see that the x squared almost entirely cancels itself out, because when we take x squared as common, we get v squared minus 2 whole divided by x squared v. Canceling out the x squared, you get v squared minus 2 by v is equal to v plus x dv by dx. Now let's continue by simplifying. V minus 2 by v is equal to v plus x dv by dx, canceling out the v's. And now here is the important part. We have to do the variable separable method. Since we have dv up there, we can make it, yes, we can say v dv is equal to minus 2 by x dx. Simply moving the variables around to make it with the same variable on either side. Now when we integrate both sides, we'll get v squared by 2 is equal to minus 2 ln x plus c. Going ahead and substituting in y is equal to vx, v is equal to y by x into this one, we get y squared by 2x squared is equal to minus 2 ln x plus c. Now since we have a point right here, which is 1 comma 2, we can substitute that in here. So 4 by 2 is equal to minus 2 ln 1 plus c. C is equal to 2. Therefore y squared is equal to 2x squared times minus 2 ln x plus 2. I just moved the denominator to the other side to cross multiply, and we get our function f of x in terms of y squared. Up next, we are asked to find the values of m when the points of zero gradient, basically the maximas and minimas of this curve, lie on two straight lines in the form of this. So to do this, let's let dy by dx equal to 0. So let's write that out here. Let's let dy by dx is equal to 0. So that means that y squared minus 2x whole divided by xy is equal to 0. So y squared minus 2x is equal to 0. And this means that y squared is equal to 2x. Now let's compare this, or let's finish this off. We have y is equal to mx. So to achieve that, we can do y is equal to root over 2x squared. Forgot the x squared before this, but just remember the x squared. And this means that y is equal to x root 2. And comparing this to y is equal to mx, we say that m is equal to plus or minus root 2, since the square root function in this case makes a plus or minus sign next to it. So the values of m are plus or minus root 2. And that's section A. Let's move on to section B, where we will try to solve questions in as little space as possible to see if we can actually get this done without using extra pages. So let's start off with 10 part A, finding the roots of this equation. So cos squared x is equal to 3 sine squared x, which means that 1 by tan squared x is equal to 3, tan squared x equal to 1 by 3. That means that tan x is equal to plus or minus 1 by root 3. And this means that x is equal to pi by 6 or 5 pi by 6. Now, of course, because it's a unit circle, you have all 4 values that can technically be used for this, but since we're constrained from 0 to pi, these are the only 2 values that we're allowed to use. Moving on to part B. Find the roots of the equation find f dash of x for this function. Now, of course, we can just straight differentiate it, which would give us f dash of x is equal to 2 cosine of x times the negative sine of x by chain rule minus 6 sine of x times the cosine of x again by chain rule. Now because both of these are negatives, we can make this minus 8 sine x cos x, and to make it a little less bulky, we can equate that to minus 4 sine 2x, since sine 2x equal to 2 sine x cos x. So that's our final answer there. Part 2 is finding the coordinates of the points on the graph of y is equal to f of x, where f dash of x equal to 0, which means we're looking for the maximas and minimas. So we're saying minus 4 sine 2x equal to 0, and that means that sine 2x equal to 0, and since we're dealing with 2x and not x, it lies from 0 to 2 pi. So when is sine of alpha 0? When 2x is equal to let's see here, when 2x is equal to 0, when 2x is equal to pi, and when 2x is equal to 2 pi. This means that x is equal to 0, pi by 2, and pi. Now I apologize for solving it in such a small spot, but I hope it makes sense what exactly we're doing. And this is all simple answers, so hopefully it's easy enough. Moving on to part C, where we actually do need a tiny bit of space, but I think we can just fit that in here. So we are given the graph y of mod f of x, y is equal to mod f of x. So first of all, let's write out our points. We have, let's say this is pi, or since we're dealing with from 0 to pi, right here, we can just go ahead and mark our maxima as pi here, maximum x value as pi. Let's let this be pi by 2, and let's try to divide this as best we can into pi by 6 and pi by 3, and this is pi by 4, and again right here. And I'm not going to label these, and even though they're approximate, on your actual graph you'd probably want to be a little bit more exact, maybe use a ruler and finish it off. But let's start off with what happens when x is equal to 0. In this graph, cos of 0 is 1, and 3 sine of 0 is 0, so 0. So at x is equal to 0, y is equal to 1. Now next we have a maxima or a minima at 0. So that means that from here on out it either goes down or goes up. So let's see what happens at pi by 6. At pi by 6, we end up with 3 by 4 minus 3 times 1 by 2, or 1 by 4, which gives us 0. So at pi by 6, we have the value of 0. So that means that our curve goes down this way. Now what happens at pi by 4? Pi by 4 is a pretty common, easy to remember value, guys, since it's 1 by root 2. So 1 by root 2 whole squared is 1 by 2 minus 3 times 1 by 2 is equal to minus 1. So at pi by 4, we go to minus 1. But since we're dealing with the mod graph, we go straight back up here. So I guess the curve would be like this. Now it keeps on increasing until we hit pi by 2. So what happens when we insert pi by 2 into the equation? So cos of pi by 2 is 0, minus 3 pi by 2, which is minus 3, 3 sine squared pi by 2, which is 3 times 1, which is minus 3. So then mod of f of x is going to be 3. So at pi by 2, we have 3. So let's call this 3. And let's finish the curve. And so that's how it's going to be. Now with this, you guys might realize that it's essentially going to be a reflection of the curve about this x is equal to pi by 2 line, since it is a trigonometric function, which means it's oscillatory. So that means that at pi, we're again going to have the value of 1, and at pi by 6, it's going to be 0, and then from pi by 2 to not pi by 6, sorry, 5 pi by 6 is going to be 0, and that's it. So in your exam, you'd label these points pi by 2, comma 3, pi, comma 1, 0, comma 1, pi by 6, comma 0, and 5 pi by 6, comma 0. And what's very helpful is always just plotting out as many of the points as you can, because we're dealing with trigonometric functions, dealing with pi by 6, pi by 4, pi by 3, pi by 2, and the rest of the pi values should get you far enough that you make a very clear answer. And now we're asked in part D to solve the inequality f of x is greater than 1. So I will use pink for this, and we'll draw a straight line where y is equal to 1. See that from 0 to pi by 6 it's less than 1, and from pi by 6 to pi by 4 right here it's less than 1. But from pi by 4 up to 3 pi by 4 it is greater than 1. So pi by 4 comma 1 and 3 pi by 4 comma 1. Therefore, by the graph for mod f of x greater than 1, x lies from pi by 4 to not equal to 3 pi by 4. That's it. And make sure that it's greater than, not greater than or equal to, because greater than or equal to does not satisfy this greater than sign over here. And that's it. So moving on to the next question, question number 11. Consider a 3-digit code ABC where each of A, B, and C is assigned one of the values. Total number of possible codes given that each value can be repeated. This means that you have 3 digits and you have 5 values that can go here, 5 can go here, 5 can go here, which means 5 cubed, which is equal to 125. And that's now for part 2 of the equation, we are assuming that no value is repeated. So for this, when we have 5 digits, that means we can have 5 unique digits here, we have 4 unique digits here, and 3 unique digits here, which is the same as 5p3, which is equal to 5 times 4 times 3, which is 20 times 3, which is equal to 60. So math paper 1, you guys don't get a calculator, so it means that you're going to be doing a lot of mental math actually, so make sure you guys have those multiplication tables down pat. Don't depend too much on your calculator, because at the end of the day, simple multiplication is something that's actually useful in life, unlike unfortunately most of what we learn. But continuing on to the second part, given p of x as a function of this, we are asked to we are assuming that no value is repeated. We are asked to find an expression for b in terms of a. Now this seems interesting. So for b is the coefficient of x squared, and so a is the coefficient of x squared and b is the coefficient of x. So this basically means that you need to find out what b would be in terms of a. Now to do this, since we have 3 constants, I think the best thing to do is first to eliminate one of them. And we can do that by finding the zeros of this polynomial. Now we can write this as x plus 1 times x plus 2. And that means the zeros are minus 1 comma minus 2. So if we say p of minus 1 minus p of minus 2, we'll get rid of this c and this x cubed, or not that x cubed, but we'll get rid of the c, which allows us to find an equation just in terms of a and b. This is where a significant amount of reasoning, logic, and a lot of understanding is required. Otherwise, you guys might get stuck. So let's zoom in a little bit so we can write. So p of minus 1 minus p of minus 2. So let's see what happens when you substitute that in over here. We end up with minus 1 plus a minus b plus c. That's the first one. And the second one is minus 8 plus 4a minus 2b plus c. And there is a negative sign between those, so let's just move it apart and write that in. And this means that you will get you will get a 7 minus 3a plus b is equal to 0. Since these are the zeros of the polynomial, you have the right hand side of the equation as well. That's where these zeros are useful, rather than plugging in any arbitrary value. You have the value of the output as well, because 0 minus 0 is still 0. Now we can write, we're looking for b in terms of a, so b is equal to 3a minus 7. Now let's move on to part 2. Now we have to show that the only way to assign the values is a is equal to 4, b is equal to 5, and c is equal to 2. Okay, how about we try this? Let's go ahead and try to substitute in every value of a. So if a is equal to 1, then b is equal to minus 4. And that's automatically wrong, isn't it? Because the only numbers you get is 1, 2, 3, and 1, 2, 3, 4, and 5. There's no negatives. Now, if a is equal to 2, then b is equal to minus 1. So again, it's incorrect. If a is equal to 3, oh, look at that. Finally, you get b is equal to 2. How nice. But now let's look at what c has to be. So if we plug this into the actual equation for minus 1, let's say, minus 1 plus 3a minus 2 plus c is equal to 0. And that a is 3, so it just becomes, it gets ignored. We will get c is equal to 0 here. And 0 is also not a valid number. So it's incorrect. Did I do that right? Yeah, exactly. So c is also incorrect. Now let's do a is equal to 5. Then b is equal to 15 minus 7, which is 8, which is also not possible. Since a cannot be equal to 1, 2, 3, or 5, a is equal to 4, therefore b is equal to 5, and c is equal to 2. And that's it. So this you'd have to write out in a few more lines, make it more neat as a case-by-case basis. Say you're identifying each case and you're solving it. So it'd be like that. Now, we're expressing p of x as a product of linear factors. So let's see if we can write that out right here, shall we? So since we already have a, b, and c, let's call this x plus, I don't know, alpha times, and we already found here x plus 1 and x plus 2 are the factors of p of x. X plus 1 and x plus 2 is equal to x cubed plus 4ax squared plus 5x plus 2. Right. Now let's compare the equations. Well, I think it's pretty much instantaneous, isn't it? The constant here is 2, and the constants here are 2, 1, and alpha. So this means that 2 times 1 times alpha is equal to 2, which means that alpha is equal to 1. So let's write out here. P of x is equal to x plus 1, or here, let's get some more space. P of x is equal to x plus 1 times x plus 1 times x plus 2. And that's it. Hence or otherwise, sketch the graph of y is equal to p of x, clearly showing the coordinates of any intersects. So this is a special case of a cubic polynomial, or any polynomial really. It means that you have x plus 1 whole squared times x plus 2. So this means that it touches the y-axis, so y is equal to 0 at x equal to minus 1 and x is equal to minus 2. And if you guys remember, a cubic curve has two bends. Two bends. So this means that this x is equal to minus 1 value, since it's a square, is a tangent. It's not an intersection. So let's try this out. 0 or minus 1 comma 0 is a tangent. And another point that's important is right here, minus 2 comma 0. But here it's actually an intersection. So let's say it goes like this, curves back down, goes up, crosses the x-axis, crosses the y-axis, and yeah, it's kind of a wonky curve, but it's okay. Now, another thing you want to do is find out this y-intercept, which is 0 comma 1 times 2, guys, 2. So that's your y-intercept, that's your x-intercept. Now the last thing you want to do is see if you can find the maxima point right here, because you don't know exactly what the mark scheme entails, and since you're plotting a graph, you always write out the maximas as best as you can. So x cubed plus 4x squared plus 5x plus 2, differentiate it, 3x squared plus 8x plus 5 is equal to 0. Let's use the quadratic solver. Minus 8 plus or minus root over 64 minus 4ac, which is 60, by 2a, which is 6. So minus 8 plus or minus, let's see, plus or minus 2 by 6, which is either minus 1 or minus 5 by 3. Now you'll see that minus 1 is already given here as a minima, and the maxima therefore must be minus 5 by 3. So this is going to be minus 5 by 3, comma, what happens when you plug this in? Minus 5 by 3 plus 1 is 4 by 9 times 6, 1 by 3, which is 4 by 27. I really hope I'm right with that math. 1, 3, 2, 3, yep. Yeah. So how I got this value is just by plugging minus 5 by 3 into this equation. Minus 5 by 3 plus 1 is equal to 2 by 3 whole squared is equal to, or minus 2 by 3 whole squared, which is 4 by 9. And then x plus 2 gives you 1 by 3, and multiplying those two together gives you 4 by 27. And that's it. Just label this p of x and you're done. And we are on our last question, guys. Question number 12. Let z of n be the complex number defined as z of n is equal to n squared plus n plus 1 plus I for n in natural numbers. Find the argument of z naught. So first of all, let's write out what z naught is. Z naught is equal to 0 plus 0 plus 1 plus I, which is 1 plus I. This means that the argument is tan inverse of the complex portion, which is 1 by 1, which is tan inverse of 1, which is equal to pi by 4. That's it. Arg of z naught is equal to pi by 4. Up next, we are asked to write an expression for arg cn in terms of n. So let's use the same logic here. Tan inverse, coefficient of complex is 1, coefficient of normal is n squared plus n plus 1. So coefficient of real is n squared plus n plus 1. And that's it. Arg zn is equal to this. Now, okay, let's move that over, make it a little neater. Okay. Now, we're given w of n is the product of the z's until the n. Show that tan inverse of a plus tan inverse of b is tan inverse of a plus b by 1 minus ab. So for this, what we're going to do is let tan inverse of a plus tan inverse of b equal to theta. Now I'm writing tan inverse, you can also write arctan, same thing. Now what happens when you do tan theta? Tan theta is equal to tan of tan inverse of a plus tan inverse of b. Now tan theta, we know the formula for tan of a plus tan of b, which is we know the formula for tan of a plus b, sorry, and that is tan of a plus tan of b by 1 minus tan a tan b. So that here would be tan of tan inverse of a plus tan of tan inverse of b whole divided by 1 minus tan of tan inverse of a times tan of tan inverse of b. Yes, I know, very, very long and tedious to write, but it's okay. Now let's take the theta and do tan inverse on both sides. So tan inverse of tan inverse of a gets cancelled to a plus b. That becomes 1 minus ab, and that's it. Hence shown. That's it. And you can write theta is equal to theta, and then say that that proves that LHS is equal to RHS. Hence, or otherwise, show that arctan of W1 is equal to arctan of 2. So I'm going to write that down here because we might need a little bit of space. I'm not sure. But honestly, I think the easiest way to do this is just to solve for W1, which is Z0 times Z1. We are given an otherwise. If you had to do it like this, I guess you could take the arguments and say argument of Z1 plus argument of Z2. But since we are given the option, let's just do this. So Z1 is 1 plus I times Z1, or Z0 is 1 plus I. Z1 is 1 squared plus 1 plus 1, which is 3. So 3 plus I, which is 3 minus I squared, which is 3. Oh, sorry. Yeah. Which is 3 plus 4I minus 1, which is 2 plus 4I. And now the argument of W1 is equal to the complex binomial, which is tan inverse of 2. Hence shown. That's it. And now we have the big one. Prove by mathematical induction that arg omega n is equal to arctan of n plus 1. Mathematical induction almost always has a huge number of steps and a huge number of places to go wrong. So keep an eye out. And this is a 10-mark question, guys. So yeah, we can't lose this one, can we? So the first step of any mathematical induction is for n equal to 0. Let's prove it. I'm going to start calling it omega because that's more useful to me, but omega 0 is equal to z0. So arg of omega naught is equal to arg of z0. And this means that arg of omega naught is equal to arg of 1. Oh, sorry. Tan inverse of 1. I meant to write. So tan inverse of 1. And therefore, for n equal to 0, the statement arg of omega n is equal to tan inverse of n plus 1 holds true. Now let's go ahead and write for n of k. For n of k, n equal to k, omega k is equal to z1, z2, all the way to zk. And we are going to assume that the statement is true. Let's write it out. This means that arg of omega k is equal to tan inverse of k plus 1. So that's just what we're going to write, and we're going to leave it at that. Next, we're going to write for n is equal to k plus 1, omega k is equal to z1, z2, z3, all the way to zk and zk minus 1. So k plus 1, arg of omega k plus 1 is equal to arg. Now, what happens if we write k plus 1 as z0, z1, z2, z3, all the way to zk times zk minus 1, or zk plus 1, sorry. That means that we can write it as omega k times zk plus 1, right? So we can write it as arg omega k plus arg zk plus 1, using the properties of arguments where they add together when they multiply. Now this means that we can apply our function. So let's use our previously made equation. Let's call this 1, which is equal to tan inverse of k plus 1 plus arg of zk plus 1, which is going to be tan inverse of 1 by k plus 1 whole squared plus k plus 1 plus 1. And we have to write on the side using 1 and arg of omega n is equal to tan inverse of 1 by n squared plus n plus 1. Make sure to get those reasoning steps. Since this is mathematical induction, we are trying to prove something, we need to make sure everybody understands it. Now let's use our tan of a plus tan of b for tan inverse of a plus tan inverse of b formula, which is tan inverse of k plus 1 plus 1 by k plus 1 whole squared plus k plus 1 plus 1. Correct? Yes. And 1 minus k plus 1 by k plus 1 whole squared plus k plus 1 plus 1. Big tedious equation, right? Lots of places for mistakes. So watch out, guys. Take it slow. There's no reason to rush in this final step. You're gonna go back and check the paper after this, but for now, take it slow. Make sure you don't mess up. Tan inverse of k plus 1 and this k squared plus k plus 1 whole squared plus k plus 1 plus 1 can be written as k squared plus 3k plus 3, I believe. Yes. Whole divided by k squared plus 3k plus 3. And so what we did was we just brought it to the numerator plus 1. Don't forget that. Like I said, a lot of places for mistakes. Every step you go through, make sure you're checking and make sure you're finishing it off. And now you have, so let's bring this to the numerator as well. So k squared plus 3k plus 3 minus k minus 1 by k squared plus 3k plus 1. This is equal to, ooh, looks like we're running out of space, huh? Tan inverse of, we'll cancel out the denominators and finish off the numerator. So when we expand the brackets, we will get k cubed plus k squared plus 3k, which is 4k plus, or 4k squared, sorry, plus 6k plus 3 plus 1 is 4. Whole divided by k squared plus 2k plus 2. And now, I mean, this seems kind of like without a wall, doesn't it? But this cannot be factorized. So that means that we can't cancel out things either. So how about we try polynomial division? K squared plus 2k plus 2, k cubed plus 4k squared plus 6k plus 4. So k, get k cubed plus 2k squared plus 2k, 2k squared plus 4k plus 4 plus 2. And that's it. So that means if you cancel out this denominator and this numerator, you'll get k plus 2. So we are really running out of space. Okay, let's go ahead and add another page, I guess. So it just duplicated a page for me. Oh, nice. I will copy paste this. So I'll copy this last step that we've written all the way to other slide or other page rather. Control V. And now we have our paper. Now we can write it out as tan inverse of k plus 2. And we remember our beginnings, right? Which was arg omega k plus 1. Arg of omega k plus 1 is equal to tan of k plus 2, which is arg, zoom out a little bit, omega k plus 1 is equal to tan inverse of k plus 1 plus 1. Hence proven that for any arg of, let's go back to w n, for, no, you have to write for any n, n arg of omega n is equal to tan inverse of n plus 1. Put that in the box and say bye-bye to your examination paper because you are done. And that is it for this video, guys. Hope this was useful. I'll be posting a paper 2 in a little bit. And that's it, guys. Have a nice day and goodbye, guys.